So this sampling distributions video, it is best if you have a good understanding of a normal distribution, z-scores, and the unit normal table. So I would go back and watch those videos if needed. So sampling distributions are important because we normally cannot observe an entire population. And so the sample, taking a sample allows us to estimate what is happening in our population. So it's very important for inferential statistics and hypothesis testing. As a quick reminder, our normal distribution is one where we have a symmetrical distribution. It's unimodal, and the majority of our scores are in this between -1 and +1 standard deviations from the mean, but there is, we can estimate these probabilities. So this is in terms of standard deviations from the mean, and this is referring to observations or scores for a population. Our empirical rule is that about 68% of scores fall between -1 and +1 standard deviations, and that 95% fall between -2 and +2 standard deviations, and that 99% of our scores or observations fall between -3 or +3 standard deviations from the mean. And this is again for the population. So sampling distributions are different because we're talking about a sample statistic. I'm focusing on means for the purpose of this video. So I'm looking at the mu. I'm not talking about a sample proportion. So I'm focusing on this sample mean for this video. So for sampling distributions, we're talking about a theoretical distribution. So if we were to infinitely, repeatedly random sample, get random samples from a population, and we graphed out the mean of those random samples, we would get a normal distribution. And actually, it doesn't matter if the variable of interest or observation, whatever it is not normally distributed. So the central limit theorem is we can make this assumption that if the sample is large enough, if samples are large enough and we repeat them enough, we approximate a normal distribution. So even if we're looking at a distribution that only has two options, if we're looking at a binary distribution or a binomial distribution, we can still say that there is a normal distribution of the samples. So we can use this information again to make inferences about a population. Now, the center of a sampling distribution is the mean of the means of the repeated samples. It's also the population mean. So the idea is that with this sampling distribution, we're estimating a true population mean, or we're getting as close as we can. So this table is just to show the differences between normal distributions and sampling distributions. You'll notice that in that top row, the main difference is that we're talking about scores or observations for a normal distribution. But for a sampling distribution, we're talking about a sample statistic. And again, I'm focusing on means for this video. So we're no longer talking about individual scores, we're talking about a mean of a sample. And then this sampling distribution would have the infinite number of means. So the center of the distribution for the normal distribution is the population mean, and that holds true for the sampling distribution, but it's also the mean of all the means, of all the sample means. And then the empirical rule applies for both. The standard deviation is no longer something that we talk about in the sampling distribution because we're not talking about individual scores. We're now talking about samples. So the standard error of the mean, it's the variation between our samples, but more importantly, it tells us how close our estimates are to our population mean. So the smaller the standard error of the mean, the better our estimation. So if you have a lot of standard error of the mean, you're saying that there's a huge variation in our sample means. And so we're not getting a very good estimate of our population. For the sampling distribution of means, you'll notice this looks very similar The only thing that's different here is that we're talking now about samples. So we still have a population mean in the center of this distribution, but we're now talking about standard errors of the mean. So the standard errors of the mean fall in the same way that the standard deviations do, but again, they mean different things. So imagine that procrastination is normally distributed in the population of Fresno State undergrads. And again, it doesn't have to be normally distributed. That was just the example I used from the normal distribution video. We collect procrastination scores from 100 students. We now have a sample. This is a sample. So we need to calculate our standard error of the mean. When we have our population standard deviation, we can just divide that by the sample size, square root of the sample size. We don't usually have that, so you can use the standard deviation from the sample instead. But here we have our population standard deviation. So we take 7, which is our population standard deviation, and we divide that by the square root of n, which is 100. And so we get 0.7. So that 0.7 is our standard error of the mean. And our population mean is in the center here. So we can put 70 as our population mean. And then we can draw this out just to visualize it. And we're just going to use the same process we did for normal distributions, where we say the mean plus 1 standard error of the mean is 70.7, minus 1 standard error of the mean is 69.30. And then we do the same for -2 and +2 standard errors of the mean, and the same for -3 and +3 standard errors of the mean. So we're just using this standard error of the mean and adding it or subtracting it from the population mean. And again, we're talking about samples. So these are sample means. So if we collect scores from 100 students, we get a mean of 72.2. So that's 2.2 points higher than our population mean. So we want to know, how likely is it that we would get a sample mean for procrastination that is more extreme, that is that or more extreme than the 72.2? And what I mean by that is, when I talk about extreme, I'm talking about farther into the tails. So further from the mean equals extreme. So the idea is the same as what we talked about for normal distributions. But now for our z-statistic, we're getting the mean minus the population mean. So our sample mean minus the population mean over the standard error of the mean is how we calculate this. So we take our 72.2, which is our mean that we calculated. We subtract 70, which is our population mean, divided by our standard error of the mean that we calculated on the previous slide, and we get 3.14. So that's our z-score, or z-statistic for our sample. So we can see right away that this is pretty extreme. This is pretty far into the tails. And so we know that it's unlikely that we would get that high or higher of a sample mean by chance. So when we get into hypothesis testing, we're going to talk about this idea of sampling error again, and that and what we're trying to do is that we want to see, is our sample so extreme that we think it's not just sampling error, that it's not just because of sampling variation? Is it meaningful? Is there something different about our sample? So when we talk about getting that information, how likely is it that we would get the sample mean for procrastination that is as or more extreme than 72.2? We have our z-score. This is our little distribution here. And we want to look for this area. So we're looking in the tail of the distribution. So in our unit normal table, we look for 3.14, which is here. And we want to look in the tail, because that's where this portion of the distribution is that we're looking. So it's when you're looking for the tail end and it's less than half of your distribution, that would be the tail. So here we can see that we have a very, very small number, 0.0008. So that, if we were to make that a percent, we would move our decimal points 2 to the right, and so that would be 0.08%. So we're saying that there's a 0.08% chance that we would get this this sample from this sample distribution. And that is our probability value, our p-value. So the next videos go into hypothesis testing, which is where we're going with this. But that is the idea of a sampling distribution. So we're talking about the likelihood of our samples.